Hello. In this video, we are going to talk about limits of functions of 2 and 3 variables. I would like to start this video with the formal definition of limit of function of 2 variables. So, let f be a function of 2 variables whose domain is D, and we also assume that the D contains points that are close to the point AB, which will be our limit point. Now, we say that the limit of f of xy as xy approaches to AB is L, and we use this mathematical notation, limit, below it xy approaches to AB of f of xy is equal to L, if the following condition is satisfied. For any epsilon positive, there exists a positive number delta, so that for all xy in the domain which satisfies this condition, which is x minus a squared plus y minus b squared under the square root, the sum, is less than delta, then f of xy minus L, the absolute value of this quantity must be less than epsilon. Now, let me illustrate this formal definition. So, here we take a domain of our function. So, D represents the domain of f. And for simplicity, we are going to assume that the point AB is in our domain. If you notice from this formal definition, the AB doesn't need to be in the domain of the function. But in this illustration, we assume that it is in the domain. And then we mark around this AB a disk of radius delta. Now, the definition of limit says if I choose a point in this disk, then the f will take this point to an interval of size epsilon around the number L. Now, what does it mean taking a point xy within this disk? It means that the distance between AB and xy is less than delta. Now, the distance is given by this relation. So, this relation less than delta means that the point is in the disk. And then f takes xy to this interval. It means that the distance between the f of xy and L is less than epsilon, which corresponds to this condition in the formal definition. Now, let me also explain you how we generalize this limit definition for functions of 2 variables to the limit definition of functions of 3 variables. Now, this time our points have 3 coordinates, so A, B, C. So, as x, y, z approaches to A, B, C, we say that the limit of f is equal to L if the following condition is satisfied. So, again, for any positive epsilon, we should be able to find a positive number delta which satisfies the following conditions. So, if the distance of the xyz to the point ABC is less than delta, then the distance between f of xyz and the L is less than epsilon. So, the only difference between the notions of limits of functions of 2 and 3 variables is this distance formula. So, the way we calculate the distance in 2 dimensions and 3 dimensions is different. Okay, now let's talk about some properties of limits. Here you are familiar with these properties from functions of single variables, and I'm going to explain these properties for only functions of 2 variables, and they easily generalize to functions of 3 variables. So here we take 2 functions f and g with 2 variables. the limit of f is L and the limit of g is M, we also take a constant k. Now, our first rules is about the sum and difference of two functions. So if we have limit of f plus g, then it is equal to limit of f plus limit of g. If we have difference, limit of f minus g, it is equal to limit of f minus limit of g. Our second rule is about product between a constant and a function. So limit of k times f, it is equal to k times limit of f. Now, third rule, it's about a product of two functions. So limit of f times g is equal to limit of f times limit of g. The fourth rule is about the quotient. Now, we have to be careful about the function in the denominator. Here it is g. We have to make sure that the limit of g is not equal to 0. Now, if this condition is satisfied, then the limit of f over g is equal to the limit of f over the limit of g. Now, the last rule is about the powers of functions. If here we assume that n is a positive integer, now the limit of f to the power n is equal to the nth power of limit of f. In other words, L to the power n. Next, we are going to talk about techniques to evaluate limits. We have a couple of techniques, and our first technique is the direct substitution. Now, this technique uses also the properties of limits that we have just seen. So, in our first example, we'd like to calculate the limit of this two-variable function, which is polynomial. Our function is 2x squared y minus 3xy plus y squared. So if we just focus on one part of this function, which is 2x squared y, I can see that it is multiplied by 2, so which is a constant. And then I can see the x squared times y part as multiplication between the function x squared and the function y. So I can apply the limit properties, and I'm going to have the following. So 2 times the limit of x squared, it is 1, times limit of y as y approaches to -1 is -1, minus the constant 3 times x times y, and then plus 5 times y squared. Now, if we simplify this, we have here -2 plus 3, which is 1, and plus 5, which is 6. Okay. In our next example, we have this time a 3-variable function, and I'm going to use again the direct substitution, because this point here is in the domain of this 3-variable function, and the limit is going to be, so 1 over -1 and sine of 1 times -1 over 2 pi. If we simplify this, the power of e is going to be -1 over 2, and we are going to have sine of -pi over 2. So this part here, it is simply -1. So our limit is -e to the power -1 over 2. So if we move on to our next technique of evaluating limits, it is going to be rewriting. Now, if we look at this example, and if I want to apply a direct substitution here, I will face a problem because the limit point 22 will make the denominator of my function, of my two-variable function, equal to 0. So, but by simply rewriting this function, I can remove this problem. And in order to rewrite this function, I'm going to multiply it with the conjugate of the denominator, which is square root of x plus y plus 2. And then the numerator will be x plus y minus 4 times square root of x plus y plus 2. And the denominator will be difference of two squares, which is x plus y minus 4. Then I simplify the expression x plus y minus 4 from the numerator and the denominator. So after rewriting, my function becomes square root of x plus y plus 2. So the limit given in the question x plus y minus 2 is equal to limit of this function square root of x plus y plus 2, and by direct substitution I can find this limit. So it's 2 plus 2 inside the square root, and then plus another 2, so which is 4. Okay, so let's have a look our next technique, the squeeze theorem. This technique should be familiar to you from functions of single variables. So, and the exact statement of the squeeze theorem generalizes to functions with more than one variable. Here I state only for functions of two variables. So let's say that we have three functions f, g, and h with two variables. If we have this order between the functions, f is the smallest, g is in between, and h is the largest for all x, y, which are close to AB. And AB is our limit point. And we also assume that the limit of f as xy approaches to AB and the limit of h, again, as xy approaches to AB exist. They are equal to the value L. Then the squeeze theorem says that the limit of g as xy approaches to AB is also L. Now, you can generalize easily this squeeze theorem to functions with more than two variables. Now, let's see how we use this squeeze theorem on our next example. Here, we'd like to calculate the limit as xy approaches to 0, 0, this two-variable function, which is x squared times sine squared y all over x squared plus 2y squared. Okay. To be able to use the squeeze theorem, I need to find a function which is smaller and greater than this one when the x and y are close to the limit point 0 and 0. So let's write our function here, x squared sine squared y over x squared plus 2y squared. Okay, my first observation is the following. As you see, all the terms in this function are squared. So we can easily say that for every xy, our function is greater than or equal to 0. To find a function which is greater than ours, I'm going to do the following observation. So first, let me write a function which is greater or equal to our function sine squared of y. And why do we have this result? Because we observe that x squared over x squared plus 2y squared is always less than 1. The numerator has x squared and the denominator has x squared and plus something else, which is always positive. So I can say that the denominator is clearly bigger than the numerator, and therefore this fraction is less than 1. So our function is less than sine squared of y. Now, I have found two functions, which is one of them is smaller, the other one is greater. And this function, since it is constant, as xy approaches to 0, 0, has limit 0. And this function, which is greater, has only one variable, and which is y. And as y approaches to 0, the limit of this function is sine squared of 0, which is 0. So the conditions of the squeeze theorem are satisfied. The function which is smaller and the function which is bigger, they have both limits and they are equal. They are both 0. Then, by squeeze theorem, I can say that the limit of our function given in the question, x squared sine squared over x squared plus 2y squared, is also 0. Okay, now our last technique of evaluating limits is going to be polar coordinates. Now, before we do an example, let me remind you the relation between the Cartesian coordinates and the polar coordinates. So x is equal to r sine theta, y is equal to r cosine theta, and x squared plus y squared is r squared. And we can always assume that r is positive. Now, as xy approaches to 0, 0, so if you look at these two relations, then r has to approach to 0. But since we are assuming that the r's are positive, then r is going to approach to 0 from a positive side. So now, let's look at our example. We want to calculate the limit as xy approaches to 0, 0 of this two-variable function, which is x squared plus y squared times ln of x squared plus y squared. So, first of all, I'm going to write the function in polar coordinates. So, using this identity, it will be r squared ln of r squared. So, the limit given in the question is going to be limit as r approaches to 0 from the positive side of the function r squared ln of r squared. So now we can see clearly the benefit of using polar coordinates for this example. We have started with a function of two variables. Now, after using polar coordinates, we have expressed the same limit as a function of function of single variable. So we can use the techniques of evaluating limits of functions of single variables. And one of the most important techniques of evaluating such limits is the L'Hopital's rule. At this point, as r approaches to 0, this limit is undetermined, because we have 0 times infinity problem. So we have to do some extra work to determine this limit, and that extra work involves the L'Hopital's rule, as I said. So, but before we use the L'Hopital's rule, we have to rewrite this function. So I bring the r squared into the denominator and I negate its power. So now we have infinity over infinity undetermined form. And to evaluate such undetermined forms, we use L'Hopital's rule. So I derive the numerator and the denominator. So here we are going to have 1 over r squared times 2r, and the derivative of the denominator will be negative 2 times r to the power negative 3. And after simplifying this expression, we are going to have a minus sign, as you see. So I'm going to write it in front of the limit. The 2's will cancel out, and I'm going to have r squared. So all the r's here will simplify to r squared, and as r goes to 0 from the positive side, our limit is going to be simply 0. Lastly, we are going to talk about a technique to show that the limit of a function does not exist. So this technique is called a technique of different paths. So we take two paths, C1 and C2, which pass through the point AB. Now, we assume that our function as xy approaches to AB has limit L1 along the path C1 and has limit L2 along the path C2. And also L1 is different than L2. Now, then we say that our function does not have limit as xy approaches to AB. Now, let me illustrate this technique on this picture. So here I took two paths, so they are curves which pass through the point AB. So the path C1 is in red, and the path C2 also passes through AB is in green. Now our first condition is that the limit of f as xy approaches to AB should be equal to L1 along C1. So along C1 means as I approach to point AB using points on the curve C1 and they come closer and closer to AB, then I have a limit of f which is equal to L1. Now, the limit along C2 means that I should approach to point AB following the path, in other words, using the points on the curve C2. So I can approach from both sides as you see. And then in that case, the limit is equal to L2. Now, if these two limits are different, then we say that the limit of our function as xy approaches to AB does not exist. Now, let's see how we apply this technique on questions. We'd like to show that the limit of this two-variable function does not exist as xy approaches to 0 and 0. So let me first give a name to our function. Let's say that f is x squared minus y squared over x squared plus y squared. Okay? Now, to be able to apply the technique of different paths, I need to find two distinct paths which pass through the point 0 and 0 and which gives two different limits for f. So you should try or start with paths that are simple. So the simplest path, one of the simplest paths which pass through the point 0 and 0 is x equals 0. So then I substitute this path in my function, which means that I set x equal to 0 in my function. And our function becomes 0 minus y squared over 0 plus y squared, which is negative y squared over y squared, which is equal to negative 1. So this means that along x equals 0, the function f of xy is always equal to negative 1. And therefore, limit as xy approaches to 0 and 0 of the function is equal to negative 1 along x equals 0. Now, as the second path, I choose y equals 0. And I substitute this path in my function, which gives us x squared minus 0 over x squared plus 0, which simplifies to x squared over x squared, which simplifies to 1. So this means again that our function along this path y equals 0 is always equal to 1. So it is a constant, and therefore its limit is equal to that constant. So now we have found two distinct paths, x equals 0 and y equals 0. And along those paths, our function had limits negative 1 and 1. They are distinct. So limits are different. So then by the technique of different paths, the limit as xy approaches to 0 and 0 of f of xy does not exist. Okay, so let's look at our next example where we again want to show that the limit of this two-variable function doesn't exist. And we want to use again the technique of different paths. So let's give a name to our function. So f is 2x squared y over x to the power 4 plus y squared. So our goal is to find two distinct paths which give us two distinct limits. So we start again with simple paths. So x equals 0. Along this path, our function is 0 over 0 plus y squared, which is 0. Which means that the limit of the function as x, y approaches to 0 and 0 is 0. So along x equals 0. Now, try the other simple path which passes through 0 and 0, which is y equals 0. So f of x0 is equal to 0 over x squared plus 0. So the function along y equals 0 is also 0, which means that the limit along this path is also 0. So what does that mean? First of all, it doesn't mean that the limit of this function equal to 0. So far, we have just tried two distinct paths which gave us the same limit. But there might be still a different path which will give us a limit which is different than 0. So all you have to do is continue to look for a path which is going to give you a limit different than 0. So let us try the following. Y equals x squared. So this path passes through the point 0 and 0, because if I substitute 0 for y and 0 for x, I will have the equality satisfied. And let's substitute this path in our function. So this means that the y is going to be equal to x squared. So our function f of xy will be, in fact, f of x squared. So which will be 2x squared x squared over x squared plus x squared squared. Okay, so let's simplify that. In the numerator, we will have 2 times x to the power 4. In the denominator, we will have x to the power 4 plus x to the power 4, which simplifies to 1. So along path y equals x squared, our function is always equal to 1. Therefore, we have the limit of the function equal to 1 as well along the path y equals x squared. So now, to conclude, you can use the path y equals x squared either with path y equals x or with path x equals 0. At the end, you have found two paths. So let's say y equals x squared and x equals 0, which gave you two different limits. So here, limits are different. So the limit as xy approaches to 0 and 0 of f of xy does not exist by the technique of different paths. Hello. In this video, we are going to talk about continuity of functions of 2 and 3 variables. So let me start with a function of 2 variables. A function f with 2 variables is continuous at the point AB if the following conditions are satisfied. First, we require that the point AB to be in the domain of f. And second, we want the limit of f as xy approaches to AB exist. And lastly, we want this limit to be equal to the value of the function at the point AB. Now, if f is continuous at all points in its domain, we say that f is continuous in its domain. Now, this definition of continuity can be easily extended to the definition of continuity of functions of 3 variables simply by increasing the components of points. Now, I would like to remark that being continuous in its domain for a function means that its graph does not have any holes or breaks. So something similar to continuity of functions of single variables. Now, next, we are going to talk about some of the fundamental functions which are always continuous in their domain. So, those functions are polynomials, rationals, which are quotients of polynomials, trigonometric functions and their inverses, exponential function, logarithmic function, and the root function. So, those are going to be the commonly seen continuous functions. Now, let's study the continuity of this function at 0 and 0. Here we are given a piecewise function. F is equal to x squared over y squared. F is equal to x squared times y squared over 2x squared plus y squared if xy is different than 0 and 0. And it is equal to 1 if xy is 0 and 0. So, and we want to study in particular the continuity of this function at 0 and 0. So, first of all, we check whether the 0, 0 is in the domain of this function f. As you see, it is in the domain because at 0 and 0, the function is equal to 1. So, 0, 0 is in the domain of f, and the value of the function at 0 and 0 is 1. Next, we determine if the limit of this function at 0, 0 exists or not. So, limit as xy goes to 0, 0, we'd like to find this limit. So, let me copy the function. Okay, now to evaluate this limit, we are going to use squeeze theorem. Now, to be able to use squeeze theorem, I need to find 2 functions which are, one of them is smaller than this and then the other one is greater than this with the same limit. So, my first observation about this function is all terms are squared and in the denominator we are adding two positive numbers. So I can say that our function is always greater than or equal to 0. On the other hand, our function is smaller than y squared. So because of the following. So x squared over 2x squared plus y squared is always less than or equal to 1. In the numerator I have just x squared, but in the denominator I have 2x squared, so which is already more than x squared, and in addition to that I add another positive number to it, so which is y squared. So clearly the denominator is bigger than the numerator, so this quotient is less than or equal to 1, and therefore whenever I multiply both sides by y squared, which is always positive, so the direction of the inequality doesn't change, I'm going to have the function less than or equal to y squared. And so for the small function, we notice that the limit is equal to 0 as xy approaches to 0 and 0 because it's a constant function. Now for y squared, again, as we approach to the limit point, it approaches to 0. So by squeeze theorem, our limit is equal to 0. So now, in the definition of continuity, we have also satisfied the second condition. The limit of our function exists. Now, for the last part, we have to verify whether this limit is equal to the value of the function. Now, we observe that, so limit as xy goes to 0 and 0 of the function is equal to 1, and f of 0, 0, the value of the function at the limit point is 1. So limit is different than the value of the function at the limit point, and then f is not continuous at the point 0 and 0.